Good morning and warm welcome to all my dear students. In today's lecture we are going to see the double reinforced section. Till now we have studied the singly reinforced section, design of singly reinforced section and analysis of singly reinforced section. In today's lecture we are going to focus on the doubly reinforced section. How to design the doubly reinforced section, how to analyze the doubly reinforced section, and what is the necessity of doubly reinforced sections. These are the key points of our today's lecture. Okay, so we'll start with our topic, a doubly reinforced section. So before I start the actual topic, so let us start with the revision of our previous lecture. So we have seen there are limiting values of moment of resistance, MU limit, and for different grades of steel, these equations for MU limits are different. This means these MU limit equations are MU limit is equal to 0.149 FCK BD square. This is for Fe250. 0.148 FCK BD square for Fe250, 415, 138 not 148, and 0.133 FCK BD square for Fe500. Actually this value of 0.149 in previous lecture I have taken as a 0.148, but actually it is 0.149 because the digit beyond this 8 point is more than 5, so you have to take it as a 0.149 FCK BD square. Okay, so these are the limiting values for moment of resistance for given grade of steel. So what is mean by limiting values? Means for given depth and width of the beam, for given depth and width of beam, and for given grade of steel and concrete, the maximum moment of resistance offered by the beam will be given by this equation. Means, suppose B is equal to 230, D is equal to 400, and Fe 415, and FCK is 20. Means suppose I am using the concrete grade as F20 and using steel grade as Fe415, and width of beam is 230 and depth of beam is 400. So what will be MU limit? So MU limit is equal to, we have to refer this equation because grade of steel is Fe415. So 0.138 FCK BD square. If you substitute all the values over here, 0.138 FCK is 20, B 230, and D is 400 square. If you calculate this, you will get 101.56 kilonewton meter. So what does it mean? A single reinforced section with width 230, depth 400, and these are the material specifications. Maximum moment of resistance offered by this beam will be equal to 101.56. This maximum moment of resistance offered by this beam will be equal to 101.46. If a factor bending moment in a beam is more than this 101.56, this beam is not allowed. So this beam can resist only a bending moment or factor bending moment up to this value 101.56. if these are the design specifications. Okay, so this is MU limit. This is the meaning of limiting value of moment of resistance for given grade of concrete, for given grade of steel, and for given dimensions of width and depth. The maximum moment of resistance offered by the beam is nothing but the limiting moment of resistance, or MU limit, and it is given by these equations. Okay. Now, so for this particular beam, the MU limit is 101.56. It means it can resist the moment of resistance bending moment up to this value. But suppose in my beam, in actual beam, suppose the moment of resistance or bending moment acting on the beam due to load, due to different loads, it may be a point load along with the UDL. Due to different types of load, the bending moment or factory bending moment developed in this particular beam is suppose greater than this value, 101.56. Then what you have to do, or how will you design such beam? Now in that case, you have to increase this value of MU limit. In that case, you have to increase this value of MU limit. Suppose this bending moment, factored bending moment MD is 150 kilonewton meter, but limiting value is 101.56. You cannot design beam with this specification. So in that case, what you have to do? You have to increase the width, or you have to increase the depth, or you have to use higher grade material. See, this MU limit will increase only by increasing these terms. Is only by increasing these terms. Means FCK, B or D. If I use FCK, now it is 20. If I use M25 or M30, so this MU limit will be definitely increased. If I change the width of beam, if I change the depth of beam, right now suppose new length is 400, if I increase the depth of beam to 500, then this definitely MU limit will increase, and it will be counteracted by this design bending medium. Even suppose this value you have to increase, it will be 500, 600, then this MD will be less than this MU limit. Okay. Then he MU limit ची value तुम्हाला याच्यापेक्षा जास्त मोठी करायची असेल, so you have to increase the depth of beam accordingly. Okay. But see, changing the concrete grade for one particular beam will not be an option. Means we have three options: either increase the grade of concrete, increase the width of beam, or increase the depth of beam. But changing the grade of concrete for one particular beam will not be an option, because when you cast concrete in beam as well as slab, we cast monolithically and simultaneously. So beam as well as slab is casted at the same time. Okay. So for one particular beam, if you have to choose the different grade of concrete, it will be very difficult during the execution. Okay. So this option will not be a feasible option. Changing the width of beam. Generally the width of beam you can change, but in some exceptional cases. Otherwise the width of beam remains common for all the beams for one particular building. Means suppose I am taking one building, generally all beams of a building carries a same width, 230 or 230. Suppose you have taken the 230 mm as a width of beam, so this 230 mm width will be same for all beams. Okay, if you are taking 300 mm as a width of beam, so the 300 mm will be same for all beams. In some exceptional cases, the width of beam you can change. In some exceptional cases. Okay, so this option can be used, but in rare cases, not frequently. Then only one option remains, that is depth of beam. So depth of beam can be increased, and if you see the depth of beam in one particular building, it is different for different location. It means it will not be like that all the beams of buildings carrying same depth. It will not be possible. So beam depth depends upon their span. If the span is more, depth will be more. Okay. So you can increase the depth of beam. You can increase the depth of beam. So if you want to increase the MU limit, you can increase the depth of beam. So that is a very common option or very feasible option. Okay. Now, when I have to increase this MU limit value to reach this MD, design bending moment, I have one option that depth of beam is to be increased. But due to some architectural aspect, suppose there is some architectural restrictions, you cannot increase the depth. if you cannot increase the depth, or architect is not allowing you to increase the depth of beam beyond certain depth. Suppose architect had restricted the depth up to 400 mm only. You cannot increase the depth beyond the 400. Due to some architectural aspect, or due to some any circumstances during the execution, or due to some functional aspect. So now in that case, what you will do? We have to carry the bending moment up to 150 kN or design bending moment, whatever it is there, and MU limit is less than design bending moment. So in that case, what you will do? So this is the situation where you have to prefer a doubly reinforced section. This is the situation where you have to prefer the doubly reinforced section. Now what is there in doubly reinforced section? In doubly reinforced section, we provide the reinforcement on both sides, means on compression side also and tension side also. Okay, we provide the reinforcement on both sides, compression as well as tension. Now, in many university exam, they will ask you to write a necessity of a doubly reinforced section, right? A necessity of doubly reinforced section. So in a single line you can write a doubly reinforced section necessity as when a depth of beam or a dimensions of beam, you can include width as well as depth. Width and depth of beam is restricted due to an architectural aspect. In that case, we cannot increase the MU limit value beyond certain limit. So in that case, to resist the required bending moment, we use to prefer the doubly reinforced section. So this is the necessity, this is the requirement of doubly reinforced section. Now in doubly reinforced sections, steel is provided on both sides, compression as well as tension. Okay. So now how will you analyze this doubly reinforced section, or how to design this doubly reinforced sections? We will see. Okay. I think you will be clear with this concept where we have to prefer the doubly reinforced sections. When the design bending moment value is greater than MU limit, design bending moment is greater than MU limit, in that case we will provide doubly reinforced section. Design bending moment ची value समजा लिमिटिंग मोमेंट ऑफ रेजिस्टन्स च्या व्हॅल्यू पेक्षा जास्त असेल, MU लिमिट पेक्षा जास्त असेल, त्या केस मध्ये तुम्हाला डबल reinforced सेक्शन प्रोवाइड करायचे. ओके. So when we will provide the doubly reinforced section, when MD, design bending moment, or you can see it as a factor bending moment, MD is greater than MU limit, you have to provide doubly reinforced section. So to provide a doubly reinforced section. Now see, as I have told you, in doubly reinforced section, the reinforcement is provided on both sides. Means on tension side also, this is on compression side, and this is tension side. Okay. So this doubly reinforced section will divide two types for the analysis, just for the sake of analysis. This is normal ordinary single reinforced section, H1, plus this is a section with the additional reinforcement required for the double reinforced section. Okay, this AST is a combination of AST1 plus AST2. Okay. Now what is this AST1? What is this AST2? We'll see. So this doubly reinforced section takes a moment of resistance or bending moment of resistance equal to this MD, which is a combination of this mu1 means moment of resistance offered by this particular section plus additional moment of resistance offered by this particular section. Okay, mu1 plus mu addition. Now this mu1 is moment of resistance offered by this section. It is calculated as a single reinforced section. What is the procedure of single reinforced section? Same procedure we will follow for this particular case. But how will you calculate this mu additional? By taking this value of ASC and AST. So we will see. See, as we know, we are providing the double reinforced section when MD is greater than mu limit. So in that case, what is the additional bending moment? Mu additional means extra. Now just now we have seen the example that the mu limit value was 101 something. It was 101.56 and I have taken MD as a 150. So in that case MD was greater than mu limit or mu1. So it means there is one additional bending moment which is equal to MD minus mu limit. Or you can see it as mu1. Hey, mu1 किंवा mu limit आपण दोन्ही टाइपने डिनोट करू. So this is your mu addition. This is the extra bending moment. Now for this particular case, previous case, so this value will be something 48.44. Okay, so this is the additional or extra bending moment which is there in this particular beam. Now who will resist this additional bending moment? Who will resist this additional bending moment? This will be resisted by this ASC and AST2. This will be resisted by this ASC and AST2. Okay, so this additional compression steel and this additional tension steel, because instead of providing this ASC and AST2, if you try to resist this additional bending moment by concrete, what will happen? The compressive strain in the concrete will exceed the 0.0035 limit. Means its ultimate limit will be exceeded by the concrete and concrete will fail. So it means your section will be over reinforced section. Your section will become over reinforced section. So such condition we have to avoid. So for that we are providing this additional reinforcement on compression steel. And to counteract this compression steel, you have to provide this tensile steel at the bottom to carry the additional tension. Okay. So now this ASC, role of ASC is to generate compressive force, This ASC will provide a compressive force to resist this additional tension, to counteract or to create this additional moment. 48.44. Just for the sake of example, additional bending moment develop करण्यासाठी additional compression and additional tension ची गरज आहे. It will be provided by this ASC and this AST2. Okay. So now, if you draw the reinforcement or stress loss diagram of this particular case, this is your singly reinforced beam. Now this double reinforced beam I have divided into two parts. One is singly and this is double. And if you draw this stress diagram, this will be your usual stress diagram. This is your usual stress diagram, 0.446 FCK, and this compressive force will act here as at a distance 0.416 XU. This is your depth of neutral axis XU, and there is the tension in bottom, which is TU1. This is the CU1 compressive force. This is effective depth T, and if you see the lever arm, D minus 0.416 x. We have derived all this in the stress block parameter lecture. Okay, this is for this particular case. So now if you draw the stress block diagram for this case, this ASC will generate a compression Cu2, and it is developed by the steel, and this ASC2 will develop the tension by this ASC2. Okay, now this reinforcement will be provided at an effective cover D dash. Now these both the forces Cu2 as well as Cu2, both the forces are equal and opposite, so it will form a couple with the lever arm equal to, now you see, this is D. This is effective depth. Okay, and this is acting at a D dash, means reinforcement, center of reinforcement is at a D dash. At the same point, a compressive force, additional compressive force will be developed by the ASC, and at the center of reinforcement from the bottom, a tensile force will be developed by this AST2. Okay, so what will be the lever arm? Lever arm will be equal to, so this is D minus this D dash. See, this is D dash. So lever arm will be D minus D dash. So this Mu additional, if you want to calculate, Mu additional you will calculate by using this Cu2 or Tu2 multiplied by D minus D dash. Cu2 or Tu2 multiplied by D minus D dash. These two equal and opposite forces causing a couple which is acting on the same body, and that is what your additional moment of resistance developed by this ASC as well as AST2, and it is calculated as Cu2 or Tu2 multiplied by D minus D dash. Okay, so how to calculate that Cu2? Cu2 means compressive force caused by ASC. Okay, so the equation for calculation of this ASC is ASC into bracket FSC minus FCC. ASC into bracket FSC minus FCC. Now what is FSC and what is FCC? Explain. FSC is compressive stress in steel, and FCC is compressive stress in concrete at the level of compression reinforcement. What does it mean? Compressive stress in concrete at the level of ASC. Now see the level of ASC this, and at same level you have to find out the compressive force in concrete. So now this is the ratio of compressive stress block for the compressive force, and the compressive force at the top is 0.446, and it remains constant up to that 0.43 XU. We know that this value 0.43 XU, 0.43 XU. So this value 0.446 FCK remains constant up to 0.43 XU. We want compressive stress in concrete at the level of reinforcement. Level of reinforcement is here. Level of reinforcement is here. Means at a depth D dash, and D dash it is an effective cover. It is an effective cover, and it generally varies from 40 mm to 50 mm. means from 30 mm to 50 mm. The effective cover varies depending upon the exposure condition and the diameter of reinforcement. Okay, it means the detached value is always less than, generally less than this 0.43 XU. This detached value is less than 0.43 XU. So it means this FCC value is lies, means the level of reinforcement lies within this constant range. हे जी constant range आहे म्हणजे जिथे 0.446 FCK हे ह्या पॉइंट पासून ह्या पॉइंट पर्यंत कॉन्स्टंट आहे आणि जी रेनफोर्समेंट आहे हे येणार आहे ही ह्या रेंज मध्ये कुठेतरी मिळणार. ही रेनफोर्समेंटच्या खाली कुठे येणार नाही. इट मीन्स द स्ट्रेस at this particular level is equal to the stress at the top. Here the stress is constant है. So FCC value will be taken as 0.446 FCK. So FCC value can be taken as 0.446 FCK. But this means the effective cover is less than 0.43 XU. Effective cover is less than 0.43 XU in normal case. So up to 0.43 XU compressive stress in concrete is equal to 0.446 FCK. So FCC can be taken as 0.446 FCK. Okay. So now what about this FSC value? What about this FSC value? So now FSC value is a compressive stress in steel, permissible compressive stress in steel. We have to calculate these values from the ultimate limit given for the strain. Ultimate limit given for the strain. Okay, strain in concrete and strain in steel. And from that we have derived some values. I will directly give the values of FSC for different grade of steel and different ratio of d dash by d. These values are derived from the stress strain curve of steel and strain values at that particular level for the given ratio of d dash and d. So I will write the values. Okay, so these are the values for FSC in Newton per mm square. These are the d dash by d ratio, means effective cover divided by effective depth. So for your particular beam, you have to calculate this ratio. You have to check grade of steel and you have to take the value of FSC by interpolation. Okay, so FCC can be calculated by using this equation and FSC can be calculated by using this chart. Okay, in exam also this chart will be provided to you. Now this is for grade Fe415 and Fe500. Suppose the grade is given as a Fe250. If the grade is given as a Fe250, so this FSC value you can calculate directly as 0.87 F. By using this equation, you can calculate FSC value. FSC for Fe250 0.87 F1. Okay, so this is how you can calculate the additional compression Cu2, which is equal to ASC into FSC minus FCC. So now how will you calculate TU2? Additional tension, how will you calculate TU2? So TU2 can be calculated as again force multiplied by, stress multiplied by force. Area, stress multiplied by area, 0.87 Fy into AST. 0.87 Fy into AST. Cu2 ASC multiplied by FSC minus FCC Tu2 0.87 into Fy into AH2. How will we calculate additional moment? Cu2 or Tu2 multiplied by D minus D dash. If you are to develop the equation, we will erase this. Mu addition. This will be equal to Cu2 I will take as a ASC multiplied by FSC minus FCC into liver R D minus D dash. So this is one equation for additional moment of resistance. Then this Cu2 as well as Tu2, both the forces are equal and opposite. That means these forces are equal and opposite. It means Tu2 is equal to Cu2. So if you put this value 0.87 Fy into AH2 is equal to